So today I want to talk about Newcomb's problem. So imagine that we have a blue box and a red box. And you can see inside the blue box, and you can tell that it has 100 bucks. The red box is sealed, and you can't look inside, but you have been told by a super reliable source that it contains either nothing or $1 million. And you're offered these two options. It seems too good to be true. So the options are $1, which means take just the red box. Or $2, which means take both. The first time someone told me about the puzzle, I felt like I hadn't understood the question because it seemed so easy. What do you mean? Of course you should take both. Here's one way of thinking of it. If this was empty, then you'll do better by taking both because you'll get 100 bucks. If this one's full, then you'll still do better by taking both because you'll get 1,100,000. But now suppose that you're given some additional information about how the boxes were filled. Now, before I give you the information, this is important. The boxes are sealed. Just imagine that they're in a table in front of you. And it's not like there's some weird mechanism where if you head for both, the red one will suddenly empty. No. It's, what they have inside is fixed, and nothing you do can change that. So this is just a story about how we decided to fill them this morning. So the way it worked was that we got a personality expert to look at your file. So we handed them all the information we could about your background and as much of your psychology as we could dig up. And we asked our expert to make a prediction. So if expert predicts one boxing, red box filled. So if after looking at your profile, the expert concluded that you're the kind of person who's likely to $1, then we decided to fill the red box with $1 million. And if the expert predicting $2 boxing, then the red box was left empty. And I might as well add that the expert has been pretty reliable in the past. In fact, this experiment has been conducted thousands of times, and the expert has proved "99% accurate." And you have no reason to think there's anything special about your case. So from where you're standing, the probability that the expert will be right is 99%. So you might think that the following is true. You might think that if you $1, then it's 99% likely that the red box will be full. Because it's 99% likely that the predictor guessed correctly. And if she guessed correctly, the red box will be filled. And if you 2-box, then it's 99% likely that you'll find the red box empty. Because again, it's 99% likely that the predictor guessed correctly, and therefore the red box was left empty. Now, remember, so the issue has now been settled. So like the predictor is not going to make any changes now that you face the decision. So the boxes are there. So question, what do? Do you 1-box or do you 2-box? Yes?
How or when is the predictor predicting?
Good. So the way it worked is that she and I met this morning, and I handed her your file. And she looked at it, spent half an hour, and said, I think she's the kind of person who will. And then she either said 1-box, and then I put $1 million in the red box, or she said 2-box, and then I put nothing in the red box. We sealed the boxes. She left, and the boxes have been on the table since.
Okay, so then wouldn't it be, then you should still pick 2 boxes even if she predicts 1 box because they're already determined, right?
That's what I think. So what I think is, really, you're going to leave money lying around? But there are some people who disagree. And this is the way to think of it. This is the way to like get yourself into the mindset of someone who thinks you should 1-box. So imagine that the box people come to town, and they're running this experiment to all your friends. And some have 1-box and some have 2-box, and the next day it's your turn. So then you go and visit those of your friends who 1-boxed, and they're delighted. They're in the midst of this incredible party. They've all bought expensive champagne because of course they all got $1 million. So all of these amazing plans, startups, and then you go and talk to your 2-boxing friends who've already done it, and they're sulking with their $100. And you say, well, but you got $100. And they say, yeah, but it's only $100. And then the next day it's your turn, and you 2-box. And then your 1-boxing friends say, what? You fool. Like, you should have joined us. Like, we're the people who 1-boxed. And look at us. We're now rich. Why aren't you rich too? So let me formalize that with a conditional. Oh, do you want to say something again? Yes.
It still seems like in spite of your friends that 1-boxed their position on this, that I mean, you still you can only benefit if you pick 2 boxes. Like you're still better off.
You're still better off. I like that point. Okay, so let me first write on the board a conditional that captures the perspective of your 1-boxing friends, and then write down a conditional that captures what you just said. Okay. So okay, so these conditionals are similar to ones we talked about when we talked about time travel and free will. So this one is an indicative conditional. If you 1-box, then you'll almost certainly be rich. And this one is a counterfactual conditional. Had you 1-boxed, you would have almost certainly been rich. So let me introduce some context so we know how to assess them. So to assist this one, imagine that you're about to choose, and this is what your 1-boxing friends are saying. They're saying, 1-box. And you say, why? You say, well, because if you 1-box, you'll almost certainly be rich. And it seems to me that this conditional is true. The reason it's true is what we had said earlier. It's true because we know that the predictor is extremely accurate. So you know that it's almost certainly the case that she'll be right. In other words, it's almost certainly the case that if you $1, she will have predicted that you $1, and if you $2, she will have predicted that you $2. In other words, it's almost certainly the case that if you $1, the red box will be full, and if you $2, the red box will be empty. And therefore, it's almost certainly true that if you $1, you'll be rich. So I claim that that's true. OK, but now comes your rejoinder. What about this one? So the context in which we were to look at this one is one in which you've already chosen, and you decided to $2. And then your $1-boxing friends come back, and they say, you fool, you should have $1-boxed. And then we say, well, is this true? Is it true that had you $1-boxed, you would have been rich? I claim that the answer is no. Because so what you did is you $2-boxed, and sure enough, you looked inside the red box and it was empty. But it was empty from the start. So it's not like if you had chosen to take only one, the money would have magically appeared. No, no, when you walked into the room, the issue had been decided. When you walked into the room, it was already the case that the red box was empty. So had you $1-boxed instead of $2-boxed, $2-boxing, you would have not been rich. You would have been left with your $100. Yes?
So I think I see the paradox here, which is, so is it okay if I just say this and like maybe it'll help me to understand?
Yeah, absolutely, absolutely.
So it's like if you $1-box, then you are the type of person who $1-boxes. So the predictor will predict that you will $1-box. So if the predictor predicts that you $1-box and then you pick 2 boxes just to be safe, then you are not the kind to pick 2 boxes, right? That's it.
Well, unless the predictor is good enough, you'll go next, because a good enough predictor would have known about that extra trick, right? A good enough predictor would have said, yeah. She's the kind of person who looks like she's going to $1-box, but 2 boxes in the end, so better to leave it empty.
But then what does the predictor, so the predictor predicts that you are a 2-boxer then. Okay.
In that scenario, she would.
Mm-hmm.
OK, now, so we're going to go 1-2. But before that, let me just say something about your earlier comment. Because I think that your earlier comment points to something really important. So we have these 2 conditionals, and they point in different ways. So this one establishes a connection between $1-boxing and you're being rich. But this one doesn't. So I think the real question, the deep question is, in deciding what to do, should we go with indicative conditionals, or should we go with counterfactual conditionals? So one way to think about the argument of your $1-boxing friends is to say they are, in effect, pushing the line where the truth of an indicative conditional is enough to settle the question. But the point you made is that maybe that's not right. Maybe what wins the day is counterfactual reasoning. Maybe the crucial thing is to know whether you would have done better had you picked otherwise. And if the answer is no, then you have no reason to pick otherwise. And the reason this is linked to our discussion of time travel and free will is that there again we ask the question about whether to go with the indicative or the counterfactual. Not for deciding what to do, but for assessing the question of whether Bruno was free or whether your suicidal friend was free. So there we asked, if Bruno shoots, will he miss? And the answer was yes, because we know how the story turns out. But then there was this other issue. Suppose that he, in fact, shot and missed. Is it true that had he aimed differently, he wouldn't have missed? Well, maybe the answer to that is yes. So if you think that free will goes with the counterfactual, then Bruno is free. And similarly for the suicidal friend. So there is a connection. So maybe you think that both for the purposes of assessing issues of free will and for the purposes of decision, what matters is the counterfactual condition. Or you might think that for both purposes, what matters is the indicative condition. And I think what the view that you are voicing is that no, we should go with the counterfactual. That is the majority view amongst philosophers. But something that is a source of enormous frustration for me is that a very dear friend, who is also one of the smartest people I know, is a one-boxer. And I've never been able to convince him. In fact, normally he would be here right now talking to you about one-boxing, but he's on sabbatical in Cambridge. So maybe I can convince him to Skype in or something. I've had him in the class in the past, and it has been very disappointing, because my hope is that students would hear my side and would hear his side, but then I would convince them all. And in fact, it wasn't that easy. So it was pretty mixed in the end. OK, so 1 and 2. Oh, yes, microphone.
All right, so I think if I were actually put in this position, I'd probably be a one-boxer. I think the reason two-boxing is so, the reason everyone's like, duh, you just two-box is because everyone has this model in their head that, the past causes the present, and the arrow does not go the other way, which is, true, of course. But I think in this case, you can have a model where, I do something in the present, and that, that changes something that happens in the past, and that is pretty consistent. At least that may not be what physically happens, but if you just ignore all the physics and you just write your mathematical model out, it's pretty close, and it's better even than going with the normal notion.
I love that point. I love that point. So here's a way of thinking of it. Let's just agree that when you're deciding what to do, really what you're deciding is which of your options would cause the best outcome. So really the question of what to do is a question about how causal chains work out. So what you've pointed out is that one can make the point we made with these two conditionals in a different way. What you can say is, OK, let's agree that you're looking for the best causal outcome. But we're not presupposing anything about how causation works. So in one way of thinking about causation, it always goes towards the future. So then, of course, you should two-box, because what's in the boxes has been settled. So the issue is just what to do while leaving that fixed. So maybe we can draw a picture. So here's the world, and then at a certain time, the predictor made a prediction, and the red box was either left full or not. And then at this point, you face a choice. Say that you're in fact going to two-box. Your other option was to one-box. But in thinking about what would have happened, we're leaving everything before this point fixed. So then on that way of thinking, of course you should two-box. But what you're suggesting is, well, maybe that's not the way to think of it. Maybe the way to think of it is a situation in which, at the crucial point, had you acted differently? We consider the state of the world as it is at this point with a minor modification, which is your different decision. And then we apply the laws forward, but also backwards. And then you say, well, by applying the laws backwards, the predictor makes a different prediction. The reason I like this is because I think that that is rock bottom. So I do not think I've ever been able to convince someone who starts out thinking that way to go the other way. So it's just if that is how you really think about causation, and therefore about decision theory, then from your point of view, one-boxing is the thing to do. And I think that that is one of the reasons philosophy is so difficult. Because sometimes the rules of the game are clear. And then what you need to do is just you find a situation and you apply those rules and decide how to deal with the situation. But what happens in this case is that we've gotten to a point where it's just not clear what set of rules to deploy. Are we going to deploy the leave the past fixed paradigm, or are we going to apply the rival paradigm? And I have no place to stand, no neutral place to stand from which to say to you, use mine rather than yours. I still think you should two-box, though. OK, so 1, 2, 3. Actually, Damien should start just because he has the common good in mind.
I just wonder what you thought about this. I thought if you have the view of causation just stated about that it can work backwards, then is that not at least consistent and maybe actually entails that you still think you should go with the counterfactuals, not the indicative conditionals? It's just that you think they're different to what most people think they are.
I absolutely agree. I absolutely agree. So let me just re-say what Damien said. So earlier, I was saying the way to think about the difference between one-boxers and two-boxers is that one-boxers go with the indicative and two-boxers go with the counterfactual. What Damien pointed out is that that's only right if you presuppose the standard way of thinking about causation, where the past is left fixed. If you don't, then what you can say is, no, let's all agree that we go with the counterfactual. It's just the counterfactuals work differently, because in assessing counterfactuals, you can't assume that the past remains fixed. So I think that's absolutely right. OK, so there were 3 questions, but I think we only have time for 2. So let's do 1, and then I forgot who 2.
Thanks. What if we said the predictor was 100% accurate instead of 99% accurate? Then would the counterfactual condition be true? Like you put an X there, and I actually agree with that X, but if the predictor were 100% accurate instead of 99, then would it be a check?
I'm going to tell you what I think, and then I'm going to tell you what other people think. What I think is nothing changes. So let me illustrate with a science fiction-y way of imagining a predictor who's perfectly accurate. So imagine that the way the predictor works is that she's cloned you. So she's produced a perfect molecule-for-molecule duplicate of you and put him in an identical environment and ran the experiment on him, and then just say, well, you're going to do whatever he did. You know, that's like a pretty accurate prediction method. And then what happened is, in accordance with what your clone decided, she filled the boxes. But I think nothing changes, because it's still true that when you walk into the room, the issue has been decided. So if you leave the $100, well, you're just $100 poorer. And like, there's nothing you could have done that would have improved your situation over two-boxing. Do you want to say more?
Was your explanation of the clone trying to give an example of how a predictor could be 100% accurate?
That's right, or at least very, very close.
But then you're saying that that could still be wrong.
No. I'm saying that such a predictor would predict correctly. It's just that when you ask the question of what you should do, it's still true that what you should do is two-box. I mean, maybe you'll one-box anyway. Maybe you'll do what you shouldn't have done. And in that case, I can tell you right now that you're going to be rich. But I'm inclined to agree with what you were saying, that that is no reason to one-box, because the money is there already. So if it's true that the predictor predicted that you're going to one-box, then you have $1,100,000 there on the table. And if you leave the $100, then it's your loss. You're going to be $100 poor.
If it's 100% accurate, then you're not going to one-box. I mean, you're not going to two-box.
Ah, excellent point. Then it's like Bruno. Because here's something we know about Bruno. It's 100% certain that he is not going to kill grandfather. We don't know why. We don't know whether he's going to slip on a banana peel or lose his nerve or what. But that doesn't settle the question of what he could do, or indeed what he should do. Like maybe, for example, because it was his dream to kill grandfather, that's what he should have done. That's what would have made him happiest. It's just that we know that that's not what's going to happen. So there's a very tight link between the time travel case in this case. Okay, sorry, we only have time for one more question. I'm sorry about that. This is a very productive line of thought, actually. Oh, that was your question. Okay, so what I want to do now is explain why this is not just a party trick. Why this goes to the heart of our thinking about decision theory. As it turns out, Newcomb's problem is a counterexample to standard ways of thinking about decision theory, at least if you're a two-boxer. So what I'm going to do is I'm going to describe this way of construing decision theory, and then I'm going to tell you why Newcomb's problem raises a problem. And this has been a big issue because the task of finding a new decision theory, one that doesn't deliver the problem, has been trickier than one would have assumed. So this is a nice example of one thing that happens in philosophy. So we thought we had a very nice tool to codify our thinking about decision theory. But there's this example that shows that those rules for the game, that way of thinking doesn't quite work. So we need to suggest a new set of rules. And because what we're doing is rock bottom, it's not immediately obvious how to proceed. OK, so forget about Newcomb for now, and I'm just going to do a quick example of decision theory to illustrate how it works. OK, so suppose you're deciding what to do, and your options are party or study. Now, other things being equal, you much prefer partying. Alas, there's a test the next day, and you are mindful of the fact that there's a correlation between studying and passing the test. And although it's true that going to the party would give you, let me say, utility points, like it would make you happier, passing the exam would be so much better. So maybe I'm going to say that the difference between partying and studying is 5 points. But the difference between passing and not passing is 50 points. So let me write this down. So the value of failing the exam and partying is 5, because you get the benefit of partying, but not the benefits of passing. The value of not failing, i.e. passing and partying, is 55, because you get both benefits. The value of failing and studying is extra bad. You get nothing. And the value, sorry, of not failing and studying, that gives you 50. You don't get the benefits of partying, but you get the benefits of passing. Apologies for the bad notation. If I had written down passing, then I would have had more than one P. OK. But then, of course, there's a different issue to be mindful of, which is the correlation between passing and studying. So let me say that the probability of failing, given that you party, is 80%. So it just follows from that that the probability of not failing, given that you party, is 20%. If you study, however, then the probability of failing is just 10%, from which it follows that the probability of passing if you study is 90%. So this is what standard decision theory tells us. It tells us that the expected value of parting is the value of failing and parting times the probability that you'll fail given that you party, plus the value of not failing and partying times the probability that you'll not fail given that you party. So in other words, it's the weighted average of what will happen if you party and fail, and if you party and not fail, where the weights are given by the probability that the relevant outcome will happen given that you party. And the expected value of studying is the value of failing and studying times the probability that you'll fail given that you study, plus the value of not failing and studying times the probability that you'll not fail given that you study. And then we can just put in the numbers. So if you fail in party, you get 5. If you don't fail in party, you get 55. That is 0.8, and that is 0.2. So I did the math, and you get 15. The value of failing in studying is 0. The value of not failing in studying is 50, and this has a chance of 0.9. So that's 45. So the expected value of parting is lower than the expected value of studying. What standard decision theory says is do whatever maximizes expected value. Since studying maximizes expected value, standard decision theory says study. And I hope that sounds eminently sensible to everyone. So like in this case, it works perfectly. OK, but now for the bad news. So now suppose that your options are 1 box or 2 box. Let's say that the value of, so there are 2 things that can happen. The red box can be empty or it can be full. The value of 1 boxing with a full box is $1 million. The value of 1 boxing with a non-full box is 0. The value of 2 boxing with a full box is 1 million plus 100. The value of 2 boxing with a non-full box is 100. And the probabilities, well, that depend on how accurate the predictor is. Let me now not assume that the predictor is 99% accurate. Let me assume that the predictor is 80% accurate. In that case, what happens is that the probability of the boxes being full given the U1 box is 80%, and the probability of the box being full given the U2 box is 20%. So now let's just do the math. So the expected value of 1 boxing is the value of 1 boxing with a full box times the probability the box will be full if U1 box plus the value of having an empty box given the U1 box times the probability of finding an empty box given that you one-box. And the expected value of two-boxing is the value of finding a full box while two-boxing times the probability. You'll find a full box if you two-box, plus the value of finding an empty box while two-boxing times the probability of finding an empty box given that you two-box. And we just put in the numbers. So that's $1 million. That's 0. That is 0.8. That doesn't matter. So this is 800,000. This is 1 million plus 100. That is 0.2. That is 100. That is 0.8. And that gives us 200,100. So on this way of thinking about decision theory, we get the recommendation to one box, because that's what maximizes expected value. So if you are right, and I think that you are right, standard decision theory is wrong. Yes?
But in these two different examples, the conditions are kind of different, aren't they? Because in the test situation, at the time of the test, the probability that you pass is contingent on whether you study or not. But at the time when you choose the box, the probability, there is no difference. There's no like, it's like 100% or 0 that the box is either full or empty.
I love that point. Yes, that is a very important difference. And efforts to come up with better decision theories have attempted to build that in. So what one tries to do is say, let's just consider different possibilities about how the world is up to this point, and then just see what would happen relative to each of those possibilities. If there is one action that would deliver better results on average, where the average is weighted by how likely you think that each of those possibilities is, then go for that. So version of that is called causal decision theory. I think it's right, and nonetheless it's controversial. So that way of doing things turns out to have other problems, which we won't talk about today. But I think that what you said is exactly the way forward. Okay. So there's one other thing I want to do, but for that I need a volunteer. It won't hurt. Okay.
You want me to come up to the front?
No, you can stay there for now. I brought with me today 2 boxes. One of them is red, the other one is blue, and I filled them this morning. Let me tell you about the blue box first. In the blue box, I put $10. I would have loved to run 100, million, but my budget does not allow it. So that's in there, and that's not going to change. It's in there, and in fact, I'm just going to seal the box. OK. So that one definitely has $10. And then for the other one, I put either 0 or $100 in the presence of my wife, Carmen, this morning. And this is how I made the decision about what to do. So I didn't know which of you would volunteer, but I did have some information. So I knew that the person was an MIT student, so I knew that they would be smart. More importantly, I knew that they would have attended my lecture. And I had a plan about what I was going to say. And on that basis, I made a prediction as to whether my volunteer would take both boxes or just the red box. If I predicted they would take both, I left it empty. If I predicted they would take only the red box, I put $100 in the presence of my wife, Carmen. Now, there is one final thing you should all know about me. I do this every year. In fact, I've done it for 10 years. This is my 11th year. And I've only been wrong twice. So my reliability as a predictor is 80%. So come to the front. You can either take both, or you can just take the red one. You can take them.
Shake it.
Oh, no, you're not. That would ruin the experiment. So you can. So before taking, you have to make an announcement. So you can say, I'm getting one box, and then just take the red one. Or more specifically, the contents of the red one, because the boxes belong to my wife, Carmen.
Right?
Or you can say, I'm getting two box, and then you can take the contents of both.
I'm going to 2 box.
Okay. So you can definitely take those $10. So you're going to take them now. And now, will you also have $100?
There's nothing inside.
Well done. That's for you.
Thank you very much.
All right. See you guys next week.